Welcome back to MACSMIN 2026. It's a great pleasure to introduce Dr. Daniel Widdowson, who did PhD in our group, and his external examiner was actually Sally Price from UCL. And Dan will present his software, Crystal Geomap, which visualizes materials databases in real time. Please, Dan, over to you.
Thank you. It's good to be back. The last bit of public speaking I had to do was very different. I was in Mexico for a best man speech. And this is more my speed. It's a lot less stressful, I think, here. So let's get into it. So maybe the mouse is better.
If you wish, you could also switch on your camera.
I tried, but I don't know if my camera is working or what. So they'll just have to deal with the slides. All right. So yeah. I usually start on this slide or a slide like it, and I'm starting to wonder if it's maybe a bad way to start, but that's because we didn't really come at this. Our goal is not to revise the definition of crystal, but it's sort of a general way to start. Our goal is to roughly parameterize the space of all crystals in a way that is mathematically sensible, that follows certain rules. And those rules give rise to nice properties of our crystal descriptors, which then will make some nice maps that we'll get to see later. So crystallographers have argued over, I can use the mouse and pointer, argued over this definition of crystal. Apparently it's still not quite settled, and there are still two definitions, but that is what it is. We come at it from a different direction, and we define this thing called a periodic point set, which is about geometry. And then we use equivalence relation to make a quite strict mathematical definition. We saw a good talk the other day, yesterday or the day before, about proteins, where proteins are obviously this big mess of atoms all doing lots of complicated stuff, but usually you don't want to see all that. You want to simplify it, right? So you visualize the protein by these blobs. The blob is actually a load of atoms, right? And you gain something, which is simplicity and understanding, but you lose something because you've obviously removed some of the detail. We want to take crystals and map them to a simpler space, a mathematical space, and then we're going to put coordinates on that space. So we would also lose something. But what I like is that we have a theorem about how much you lose, right? This is called completeness, and we'll get into what completeness means. But if you have an almost one-to-one correspondence between the actual crystals and the elements of the output space, then you're losing very little. And that's why we have talked to people about the definition of a crystal, because once you have a one-to-one correspondence, you can almost say it's a definition. But regardless, let's start with this. So even 3-point sets, also known as triangles, have a great analogy with crystals in this sense that what we're trying to sort of attack. It's been mentioned today already that crystallographers are very attached to their space groups, and they define things in terms of symmetries. It's the same with triangles, right? So you could classify triangles as equilateral, isosceles, and scalene. But what if something's nearly equilateral? Are these two triangles the same or not? Maybe one's equilateral, one's not. I'd say for a lot of applications, you can understand why these should be considered like very, very similar. But if you're going by symmetries, maybe one of these is just slightly off of equilateral. So they go in different bins, but they really shouldn't be. So then someone might say, well, yeah, but up to epsilon, I can make it symmetric. But then the problem is that if I go just above epsilon, it's no longer symmetric, right? The truth is that these triangles, it's much better to visualize them on this, in this space. So this cone contains all triangles, and the special triangles with symmetries live in specific areas of the space. So the equilateral ones live on the red line, and lower symmetries live on other ones. And what it means to be almost equilateral is just that I've moved off the line a little bit. Any perturbation of a triangle that is smooth will move me around smoothly in this space. And a relevant point for later is that we can also ignore the uniform scaling of the triangle by taking a cross-section of this cone. And we want to do the exact equivalent thing to this, but for periodic point sets, not 3-point sets. So it's a harder problem, but we'll get there. I'll rush through this slide because we've probably all seen it, but we start with this definition of a periodic point set. These are the objects we're trying to classify. The boundaries there, those lines, are ephemeral. They're just there to show you the periodicity. We're concerned with infinitely repeating periodic sets of points. That's 2-dimensional, while crystals are 3-dimensional. So this is what the mathematical definition looks like. And the way that we define these periodic point sets or give them is via a cell and a motif. But unfortunately, it's quite ambiguous. And we want to do this continuous classification. We've got to take into account the fact that many different choices of cell and motif can give rise to the exact same periodic set. So even if you simplify it to just lattices, I can just choose loads of different unit cells. If I stick to one unit cell, even simpler, well, you can move around that unit cell and take very different motifs that generate the same thing. So we can't just like take the space of cell motif pairs, really. And we have to account for this fact of this ambiguity in representation, while also, importantly, our representations are, what would you call them? Descriptors of crystals. We call them isometry invariants. So isometry is really important. Rigid motion is the best way to describe two crystals as equivalent. If I can match one to the other with a rigid motion, then the two crystals are equivalent. Crystals are rigid objects. We work on isometry. There are other people in our group who are working on invariants that can distinguish mirror images. So if you're a bit scared that we're allowing mirror images because you've heard of thalidomide, well, we know, but the thing is that isometries are much easier to work with than just rigid motion. So we're talking about isometry invariants where we can guarantee mathematically that applying an isometry to our crystal does not change the output. Okay, so there's a few examples on the right there of like same or different. But the main point is that we want to avoid any reliance on the unit cell here. Of course, the atoms in this top one are like all different, but geometrically speaking, they're the same. And if I replaced all these with the exact same atom, whatever I have on the right, then the cell would reduce. But then if I apply a perturbation, the cell might not reduce. So we want continuity to be preserved even through breaking of symmetries and things like this. Things that are usually solved by a tolerance given to a space group analyzer or something like that. And here's the overall picture of, or what would you call it, the list of requirements we have for our invariant, which is going to make it nice and have nice properties. So I've represented our crystals with these finite point sets here. This top box is the space of crystals, and the bottom box is some simpler space where our coordinates are going to live, our invariants. So importantly, we want all things that are equivalent, isometric to each other, to go to the same place in the output. And we can draw a boundary around all these equivalent things and call it equivalence class, whatever. We want things that are genuinely different to map to different places. So, for example, density doesn't do that. You can easily find two crystals with the same density and they're just completely different. And we also want the gradual perturbation to always result in a smooth path in the output space, regardless of whether you have a symmetry or not. No dependence on a unit cell or symmetry or anything like that. So this is going to be the definition, the central definition that underpins everything else. This is going to be the isometry invariant used to describe our crystals, and it uses interpoint distances. So take a crystal here. This is one from the CSD, ethane. For each atom in the motif, you write down the distances to nearest neighbors in order. So in this case, if however many motif points there are, you'll get one list of distances. You might notice immediately that some of those lists will be the same. If there are symmetries, that's true, but we'll get there. Once we've got a list of distances for every every point in the unit cell. Obviously, we have to cut off this list at some point because there are infinitely many distances to measure to. We don't stop at the edge of the unit cell or anything like that. We ignore the unit cell. In this case, I've written down 4, but I think we'll show 10. So we get these lists. The next thing is to collect them into this matrix. Now, really, we could have just an unordered list of these distances, but more importantly, we need to put a weight on each of these rows. So now, we have 4 rows. The reason is that we collapse identical rows. And if you know crystallography, you know that symmetrically equivalent points will give the same row. So we have 4 rows for 4 points in the asymmetric unit. And the weights come from the Wyckoff multiplicities, the symmetric multiplicity. But you could also just say we list 1 for every motif point and then collapse and then combine the weights. And these weights should all sum to 1. Okay. Then we perform an ordering. This is a little bit of a vacuous thing to do, but it means that we can say that we have isometry invariants in terms of like equality of these matrices. So there we go. We have a matrix which represents our original structure, and that is what we call the PDD. It's just a big collection of interatomic distances that go up and up as you measure more. So, okay, yeah, quickly, we can also already see this is contains more information than another descriptor, because something like this is a classic example where you could take all the interpoint distances in an ordered list and it wouldn't distinguish these two things, but since our PDD contains more information, it can distinguish them. I'll briefly mention Earth mover's distance is what we use to compare these things, it's EMD, and it's actually a big part of the magic of why it works. So I'll briefly explain that to compare this with this, we would find an optimal matching of rows. So we compare the rows in the top one to the rows in the bottom one, and you are looking for you're looking for a matching of rows which respects the weights. So if I match one row on top, the one on the bottom, the weight should add up and is a minimum distance. It's called Earth mover's distance, so we can compare these things even though they're different sizes. I'll rush through this because we should get to the map. Time, yeah. So this thing is obviously isometry invariant, I should hope so. I've introduced this metric EMD we can use to compare them, and this is what we'd write in the theorem that shows that it's continuous, and that doesn't matter how much you mash up your unit cell, choose a bigger one and perturb stuff. As long as you perturb by a certain amount, we have a guarantee on how much the distance can change. We have very good computability. Computer scientists like this near linear time stuff, and you do need to prove it, but I'm more interested in practical performance, and this is practically it performs very well. We can do like 1,000 structures a second on a normal computer, so vast majority of databases are no problem for us to chew up. And we have this completeness statement, which I won't waffle about too much, but we can actually make a theorem that says how much information are we sort of losing. And it turns out that for most crystals, for nearly all, and that's nearly all in a mathematical sense, you can actually just go from the PDD matrix back to the original crystal. So you've preserved full information. As long as you take enough distances, then you can do it. So very, very good information. Now I should introduce this. That matrix we had is very information dense. It's good, but it's still the Earth mover's distance is probably it's a bit too slow to compare, say, 1 million crystals with each other, which would take on the order of 1 million squared comparisons. But vectors, you can do that. So we can collapse this matrix down into one vector, and computers these days are basically just vector calculation machines. They're really, really good at it. So you can use this vector for fast calculations, and we have a few results that relate these. Of course, this is less information, but it's still actually, practically speaking, very distinguishing. It still retains a lot of the information, just not necessarily all of it. Okay. The top is a bit of a statement relating the distances of one to the other. So AMD, this simpler one, can be used as sort of a cheap, inexpensive filter, and you can recompare later by the more expensive one. And then this part is rather important, so I'll talk about it. Now, if you collect interatomic distances starting from nearest to next nearest, next nearest, the distances will go up and up and up and up. If you graph that, you'll get a cube root. For three-dimensional crystal, you'll get a cube root. And we've described what that cube root is. This is the coefficient, volume per unit cell, number of motif points, and that's the volume of a unit sphere. So the values in these invariants I've been giving converge to that. And usually what we want to look at is the difference between the raw distances and the invariant, right? We'll see in a sec why that's a better thing to look at, more interesting. And using mostly AMD, but also confirming with this PDD, we're able to compare many crystals from various databases. And we have lists of cross-references, which I'll show a plot of in a second. Yeah. And we've found a whole bunch of funny errors. For example, this one, I'll try and keep time because we want to see some maps, but I found this example. This was because we compared the COD and the CSD, and we found identical geometric structures, but the COD version had a carbon and the CSD version had a chlorine. And so I looked at the publication had a carbon. So I said, oh, okay, it's a transcription error. It's a super old entry. The CIF isn't even like copy and pastable text. You have to read it. So I thought, oh, it's transcription error, right? So I pointed this out to the CSD, and the guy looked at it and said, no, that's a chlorine atom. It's the original paper has written it wrong, and we corrected it. Now, I could be wrong about this with the COD, but it's not. The COD don't want to go in and rewrite an atom. They want to take the actual data which is present in the original CIF.
Well, we can discuss that.
Sure. Yeah. But this is why the discrepancy was there. And I guess this would result in no action taken. But some of the errors we found, there have been action taken on them. When it says action, it says under investigation, that means you email the authors and they never get back to you, unfortunately. So this is what the, say, coordinate of a crystal looks like. This vector I was talking about, we've taken out the asymptotic. So if you just took the raw distances, it'd be a cube root curve. But this is how that the distances sort of wiggle around that cube root as it converges. And these ones are nice because big pores. The big pores are the things that make the peaks and the troughs. And the reason I like showing this plot is because so we have two molecules here, which are different molecules, substantially different, but they're kind of similar if you squint a bit. They both look like tripods, and nature likes to pack them in the same ways. So we have these, well, I guess there'd be four polymorphs there, two molecules. And you can see that the overall difference in the overall similarity in the shape of the crystal structure has been preserved in the similarity of these sound waves, right? You might think that if you collect these distances between atoms, well, if I change the molecule a little bit, but the packing stays the same, it'll destroy all the information, but it actually doesn't. You can see the overall similarity here, and you can see the differences in the molecules with the first few values, right? Because those first distances are very different because of the different molecule. Okay, now, I didn't know this until I just happened to stumble across it, but the COD has a list downloaded with it called duplicates.lst. And I don't know where I read this, but I'm pretty sure what they do is just look for things with the same unit cell and composition. And we are specifically, our whole thrust of our research is saying things like, that's a bad way to compare structures. To be very fair, they don't claim that they're definitely duplicates, they're potential duplicates. But what we can do is use invariants to do a proper comparison and see if there's any structures that shouldn't be on the list or ones that should be on the list. And we found both. So the top one surprised me more. Two structures with the same unit cell and the same composition, but they are not the same. So they're on the list, but they shouldn't be. Well, They should be if you explain how they got on the list, but they're obviously not duplicates, right? And the bottom is the reverse situation, two structures which are basically the same thing, but because the unit cell was different, they didn't end up on that list. All right. And here is an accurate Venn diagram of comparison between the CSD code and ICSD. If you're surprised about the overlap between CSD and ICSD, you shouldn't be. I mean, maybe you should because there's not many in there, but some crystallographers have told me, well, that shouldn't happen. There are a few. And 80% of the code is in the CSD, which I should basically expect because I think authors upload to both. They're both very good repositories of data. And all these things, except I guess materials project is a bit different. I'll explain why briefly, but there's redundant entries in all these. Whether or not it's redundant is left down to the curator of that database. Maybe there's some reason that they don't consider it redundant, but from a structural perspective and atomic types and everything, they all line up, all the coordinates are all identical. So it's redundant in that sense. In the CSD, there's a group of 37 completely identical crystals. Just get rid of 36 of them. Okay, so I'll end on this screen, but we're now going to start the demo part, so we get to see some maps finally. Right. Okay. So I want to start with the ICSD, and it'll take me just a second to set this up. So don't want disorder, and I want to show the cubic crystal system. So this is Geomap. I can choose data to plot. I can choose what plot I want and a bunch of style options. And we're going to be able to sort of fly around the space of crystals. I'm choosing cubic here because all of them is quite a lot. We'll show all of them in a second, but with cubic, you can see more of these sort of interesting features. Now I'm going to choose some values. Now this ARDA or this AMD, this vector, there are 100 components to it. So you could think, let's do dimensionality reduction to 3, but you can do that, but you lose some of the sort of realness of these values. These values are not insignificant. They don't come from a black box. So we like to do this. Even though this will be a very low dimensional projection, we'll still get to see interesting things in that projection, partly because of the continuity and invariants. If you're wondering why I'm choosing these values, so I can only choose 3 for a 3D scatter plot, it's because they're uncorrelated. If you picked the 99th, the 100th, and the 98th value, they're all correlated, so you just get a line. So we're choosing ones that are quite far apart, non-correlated. We're going to color by space group, change the size a bit, and opacity down. Okay. So I can sort of, this is kind of like a flight simulator. You have to get used to the controls, but this is what the ICSD looks like. Well, the cubic crystals in the ICSD. Let me for now I'll leave that open. So we immediately see a bunch of lines. I'll explain the lines. So mathematically, it just turns out that if you uniformly scale a crystal, then you move in this space along a straight line towards the origin. So if you scale up, then you move away from the origin in a perfectly straight line. Scale down, you go back down the line. So these lines are just uniform scaling, and we can actually see that by flying up to one of them. And I'm going to hover my mouse over it and keep an eye on this ABC here, right? That's the size of the unit cell. You see as I sort of go along the line, it's just going up and up and up and up. So it's very easy to identify why these lines exist. And each one of these lines is going to be some sort of very archetypical, popular structure type, popular with nature, I guess. So the ones in this line all look like this, right? But with differently sized unit cells. I've got a little crystal viewer over here that I can look. So that is, I believe, a diamond-like structures. We've got some sort of perovskites over here, I think. I've had to write these down so I know what they are beforehand. I believe this is a simple cubic line. Yeah, simple cubics. And of course, there's 8 atoms in that unit cell, but it's a simple cubic, so it hasn't been separated from the other simple cubics, which have 1 atom in the unit cell, which it shouldn't, because we're all about the geometry. Over here we have face-centered cubics, yep. And you get the idea. Each one of these lines is going to correspond to some popular structure. And the only reason that the lines that stand out are popular is because there's loads of structures there. I've turned the opacity down of each point on the plot. So where you see solid color, that's because many things have stacked on top of each other, right? Now, yeah, let's do this. So something interesting we can do to demonstrate why continuity matters. Well, if we fly up to this line, we see, well, zooming out, we can see these little smudges coming off the line. And you can imagine what they are. This is literally why we have made a continuous invariant. On the line, you have perfect space group, like perfect symmetry, and just off of it, you have very close but not exact. So let's try and find an example. So this is perfect symmetry, but just off the line, we have this, right? Where, as we've mentioned, so the unit cell gets extended, and then I just move the atoms a little bit, right? So just like with the triangles, when you have an equilateral triangle, you're living on the line, and then you move it a tiny bit, you move a tiny bit off the line, and that's what's happened here. If I zoom in, this might be too close, I'm not sure. Let's have a look. Oh, that's perspective. It's difficult to see, but these atoms won't be perfectly in symmetrical. It's such that you can reduce the unit cell. You could, I guess, if you have a tolerance on some sort of algorithm to do it, but we shouldn't really modify the geometry of the crystal we are given, I think. And we could go around and find many examples like this, where something's just next to a line. Okay. Next plot. So I mentioned this asymptotic, that we subtract from the raw distances and we get this wave. And uniform scaling has the effect of moving you in a straight line to or from the origin. But what we can do is divide by the asymptotic. When we divide by the asymptote, that has the equivalent thing of the cross-section in the cone of triangles, where uniform scaling doesn't matter anymore. So what we're going to see is all these lines get crushed down into one single point. Every single simple cubic will live exactly at one point in this space. So let's have a look at that. Okay, let me just clear this for a second. Controlling the speed of the camera is a bit difficult, but it's okay. So all those lines have disappeared, or at least the ones to the origin, but there are still a few more. And they've been replaced by hotspots. So we can actually just go and say, look, so this is, I believe, the point that contained all those diamond-like structures. I could fly up to this point. There's loads of crystals sitting right there. And we can check how many there are that look like that. 1,717, and you could just scroll through if I wanted to, down, down, down. Of course, they all look the same. And yes, and those structures that were similar are now doing this, where they're just smudging, so the smudge coming out of the single point, right? Okay, yes. So what about these other lines? It's a good question. Let me move the camera to the other side of the, whoop. I have to let it stabilize itself. Whoop. Okay. So we still see lines here, which aren't uniform scaling. Essentially, these lines are when a crystal is being continuously deformed by one parameter, not in multiple different ways. So say extending one side of a unit cell, just stretching the unit cell in one direction, anisotropic scaling, or possibly an atom which can be located at, say, I'll show the example in a sec. Maybe its coordinates can be something like 1/4, 1/4, 1/4 plus epsilon, where epsilon can range from 0 to 1/4, and that one parameter is all that's really distinguishing, it is changing in this sort of family of crystals, well, that results in a very consistent movement along this space because we have continuity. And why is it, you might ask, that the lines sort of bend? Like, look at this here. Right, they don't bend, they very sharply turn. So we have continuity, right? This line here goes, and then it shouldn't, it suddenly turns. This is simply because if you keep deforming, then at some point the certain nearest atoms will switch with other ones, and the rate of change will be different as you keep deforming. So it's continuous, but not smooth, I guess, right? These movements. And the next question I want to answer, but I think I'm going to show another plot. Yeah, we'll go to all ICSD to talk about this because some of these lines look a little strange. And I'd like to talk about why. So this is the whole ICSD now. We fly up to this cloud, so it's obviously a lot more noisy, but it's like sort of fly into it, a lot of the noise goes away. Oops. Okay, and this is the artifact that I want to show. Right here, this purple line. There we go, I've got it in frame. So here is where I think a bunch of spinels live. I think this is a specific family of spinels. Remember that uniform scaling doesn't matter here. If I had the other plot with the lines towards the origin, then all of these would also be lines in this direction, right? But they've all been crushed like this. The question is, why does it look so weird, right? There's obviously, this isn't like a solid line, it's dotted, and the dots are very consistent, and the little dots are consistent, but there's also consistent bold spots, like very bright spots, which are at very periodic intervals, right? We have like here to here to here to here, it's the same distance. Now, if you've been to a previous talk of mine and you've seen why this is, then stay quiet. But can anyone guess why this looks like this at all? Because I did guess. It took me a while, but in the end, I did just guess because it's possible. Very unusual. The reason is precision, right? The values in CIFs are written to 2 decimal places, maybe 3, maybe 4. So you don't get a smooth, continuous movement here. It jumps in steps. So these very bold ones will be something like the ones that were written to 2 decimal places. The ones in between those are to 3 decimal places. And you have the odd structure here and there, which has like many decimal places, and you do see a few of those. But the most popular number of decimal places to write down are shown by bold, dark patches on this line. So it's quite nice to see the result of limitations of our data plotted in a visual form. And the reason it ended up there was because I think we had strict requirements for our crystal descriptor. Okay. Now, I will do this. Another thing we could do. So we've mentioned about weird, erroneous structures, things that don't look quite right. Probably not the best thing to find them is this software, but you can by just looking at structures which are far, far away from the main cloud. So loads of things like to live here. So why is this over here? And if I hover over it, you'll find out why these things are over here. Like C720, right? So this is either the unit cell has got loads of atoms in it, or it's disorder which it couldn't be properly parsed, or it just wasn't sort of written down in the thing, or it could just be a terrible structure. What I'm not going to do is click on any of these, actually. I could, but some of them have so many atoms that it stresses my computer out a bit, and we'd have to wait. But something like this should be okay, I think. Why is this quite far from the cloud? That's why. It's just a weird structure with huge pores, right? But that's okay. Some of these structures, I think, will have errors, genuine errors in them. And that might be one way to find them, or you're probably better off just taking, is it Mahalanobis distance? The distance for sort of standard deviations from the center, multi-dimensional. This is only 3-dimensional, so you'd probably want to use all dimensions of our invariant to figure out what the weirdest ones are, and there are some really weird ones. Okay, next, let's do this. So one thing I didn't mention is that I can have multiple plots and the plots interact with each other. So we're going to show an example of that. And I want 3 databases this time. And I want to look at carbon allotropes. So that's for carbon and only carbon. And in the other plot, I'll copy over that data selection to this plot, and I want a dendrogram. Okay, I think we'll use this one for the dendrogram. Okay, so there's quite a lot of examples here. Now, keep in mind, to be fair, that there are quite a few structures where there's only carbon, but it's not actually a carbon allotrope because they didn't write down all the coordinates or something like that. But there's a lot of things which are supposed to be carbon allotropes, and what I could do is sort of hover over parts of this dendrogram to interrogate what's there. So I'll ask one more question to the audience, why not? Carbon allotropes, this really flat cluster here, which is big, so there's a lot of structures sitting there. They're all very, very similar. What is that most likely to be? Right, the most popular carbon allotrope on Earth. This is a diamond, right? So what I can do is hover over it and click and see all examples of diamond that we have in all these various databases. And they all, of course, look the same. And interestingly, I think the second sort of best cluster here is over here. I'm going to guess here that this is dangerous, but if I click on that cluster, we'll get the other most popular, the other most, second most popular graphite, right? And this is a not as flat as this because there's very little variation in the amount that diamond can vary in its measurements. Put it under pressure, but it doesn't do as much as. But graphite can change quite considerably depending on various factors. So you have sort of a higher cut-off threshold, but they're still clustered together. And I could scroll through these as well. I could see the name is graphite, so I know what they are. And we can see where these things live on our map as well by hovering. You don't notice cross highlighting. It shows us it shows us where they live. And what I like about this, and I just do this sometimes to see if I can find good looking stuff to use in the plot, can change the C to something else and get the exact same thing out. So if people have suggestions, they can give them, but I'll give one calcium carbonate. The most interesting things to plot, obviously, are things that are highly polymorphic and popular. Okay. The axis ticks are a bit strange because these are small values, but I think they're pretty well separated on the scatter plot, but we can see them very well separated by the dendrogram as well. And if we're using this in a scientific setting, I'd suggest the dendrogram, proper clustering, because this is only 3 dimensions, but we can see obviously it clusters into. There are 3 main polymorphs of calcium carbonate, and they're just immediately very well separated in no time at all. How about one more, maybe? Titanium oxide. Why not? I forgot what these look like, so I don't know how interesting they are, but I think you get the idea. Yeah. Okay. So a few other things, but really quite confident clusters, which will contain all of the examples of various polymorphs from various databases. So now I want to show the final thing. We're okay on time. I can go a bit slow. So this geomap also serves as an interface to compare crystals. This is probably better done through a command line interface, and we do have one, but it's also just here, and I can show it in the demonstration, so it's good. I think Olga has talked about ALAB, where Google created this AI genome or genome. They generated many structures. They said they were all new structures, and we've advanced human knowledge. Yeah. Then they took some of these crystals, tried to synthesize them, and were successful in some of them. But then later publications. Criticisms were published that said that a lot of those claims are not as good, and some of the crystals you managed to synthesize actually already existed. Here they are. We also found some of those crystals in existing databases, ones that people hadn't noticed. And we have published this result, but we can actually do the comparison in real time right here because it is so fast. Computers are really good with vectors. So let's compare ALAB to materials project. I'm going to ask for 10 nearest neighbors. So I'm asking, there's 43 items in ALAB there. There's 150,000 in materials project. And I'm asking for each ALAB crystal, I want 10 of the closest ones in the target database. So this will require thousands and thousands of comparisons, but it is quick enough to do right here. And I'm going to choose this one, hit compare. And what you can do, you could actually just do this, how would you say, brute force. But if you use binary search, because it's just a big list of vectors, it's like immediate, so it's already here. And we can see, scrolling through, so this one here, this ALAB crystal, we immediately just found the equivalent, an equivalent entry materials project. I believe it predates ALAB, and it's difficult to see, but this final column here is telling you when we compared the PDD matrices, we linked up atoms in one with atoms in the other. If all of the atomic types matched on each side, then we get nothing in this box. Otherwise, this sentence is trying to tell you what mismatched with what else. Say, a zinc here was replaced with something else here. But see, immediately the ALAB crystal was just found, and there's several examples of this, right? So you think that something like this being baked into the AI would be a good idea, because the AI was given two goals: create novel structures that are feasible, and it failed at the novelty test. We found things in the many things in Genome's dataset which were copies of itself. So the AI, however, they're comparing their structures to figure out if there's duplicates in the dataset potentially contaminating it. It's not working. And there's also quite a few infeasible things in that database as well. So something like this invariant, which I think is fast enough for the AI, would be of great help. And I think that is roughly where I'll stop, but I'll leave it on this slide. And if anyone wants me to plot anything specific, their favorite structures or their favorite element, we can show the allotropes of it or whatever, what have you. But that's the end of the talk for now. Okay, so thank you.
What I'll stop recording now, but answer any questions as usual.